Hello physics students. Today we're going to practice the horizontal projectile. And so projectile motion is one of those topics that can be a little challenging when you first start out. I thought this would be a good opportunity to review the key elements of any horizontal projectile. So first you'll notice that I left a lot of blanks here. We're going to go through this example and kind of make up some data to use. But I want to be clear that this process could be useful for anything that's sliding off a table, driving, if it's a car driving off a cliff, if you throw a ball horizontally, any object that's in the air with an initial horizontal velocity would be able to be solved using this method. So let's say that you have a cell phone that's going to slide off the table, and maybe it's really zipping along at, let's say, 15 meters per second. I hope you're not launching your cell phones that fast. The table could be any height. Let's say that it's a fairly tall table, maybe 2 meters tall. So maybe a shelf is a better option here. But we're going to try and determine how far away from the base of the table it's going to land and with what velocity will it hit the ground. So as always, I would recommend that you start by drawing a picture. We're going to have our very tall table. So this is 2 meters vertically. We have our little cell phone here, and it's going to be sliding off the table at 15 meters per second. And we want to know how far away from the base of the table is this going to land. That's our delta x value. So with any projectile, I'd say the second step would be to determine the components of your velocity. But for a horizontal projectile, that's really easy. It's not going up or down initially, it's only going the x direction. So by default, Vy has to be 0, and Vx is going to be whatever speed was given, 15 meters per second. So no math is really needed in that second part. Your third step is to find time, and I generally say use delta y or delta x, whichever is known, to find the time that it's in the air for. Had I said it hits the ground a certain distance away and you're trying to find the height, you'd use delta x. In this case, we know delta y, because the table is 2 meters tall, the projectile is going to fall 2 meters down. So that means that delta y is actually going to be a negative 2 meters. And we can use this to determine what the time would be. So remember that delta y is equal to Vy times t plus 1/2 a t squared. In the vertical direction, we're still under free fall here, so acceleration is going to be the acceleration due to gravity. The cell phone is going to be dropping 2 meters, so negative 2 for delta y is equal to the initial velocity in the y direction, which is 0, times time, plus 1/2 times negative 9.8 meters per second squared, t squared. 0 times any time is going to be 0, so this whole term will be 0. And negative 2 meters then would be equal to 1/2 of 9.8 is negative 4.9 meters per second squared times time squared. To get time by itself, we're going to divide by negative 4.9. And so negative 2 divided by negative 4.9 is equal to t squared. And if you notice here, negative and negative, those two negatives will cancel out. So 2 over 4.9 is t squared. If we take the square root of that answer, we can get our final time, which should be just about 0.64 seconds. So this is how long the cell phone takes to fall down to the ground. So whichever displacement we started with, you're going to solve for the other one in the fourth step. We knew delta y was negative 2, so we're going to solve for delta x. Well, that's pretty straightforward. Delta x is equal to Vx times time. There's no acceleration horizontally. Delta x then is going to be equal to the x velocity, 15 meters per second, times 0.64 seconds. And that will give you a total rate of about 9.6 meters. So the cell phone's really zipping along. It's going to fall 2 meters, but it's going to travel about 9.6 meters away from the base of the table. Now the fifth step is normally to solve for max height or terminal velocity when it hits the ground. In this situation, the max height's known because it started at 2 meters and it only drops from there. So you don't need to solve for the max height on a horizontal projectile. To find the velocity that's going to hit the ground with, we're going to use the same process that we used with the traditional or the classic projectile to find the components of velocity. We're just going to work backwards. So as the projectile comes down off the table, we can think that it's going to be falling downwards. Well, that has a horizontal velocity and a vertical component to velocity. So if I draw this a little bit neater, if we can determine what Vx and what Vy are going to be, then we can solve for the hypotenuse and the angle. Well, this is a horizontal projectile, and in the case with any projectile, actually horizontal motion is not going to change. So whatever the Vx was at the beginning, that's going to be constant all the way through. So in this case, it was 15 meters per second. Vy is going to be a little more involved. Vy is equal to the initial velocity, so our final velocity is equal to the initial velocity in the y direction plus at. We've used this equation a lot. I just put in little y's to indicate we're going up and down. If you prefer not to put the y there, that's okay. We know that there was no initial velocity in the y direction, right? It was going sideways but not up and down to begin with. So v1 is going to be 0. The acceleration is the acceleration due to gravity, so minus 9.8 meters per second squared, and it's in the air for 0.64 seconds. That will be equal to our final velocity in the y direction, which should be just about negative 6.3 meters per second. So it's going horizontally 15, and when it's approaching the ground, it's going 6.3 meters per second in the downward direction. I'm not going to worry about that negative sign right now, because if we are looking for our angle, if I find theta, I can then describe that as being below the horizontal, as opposed to when we launch a classic projectile, it's like up above the ground. So we're going to use our vocabulary words the way that we're describing where that angle is pointed to account for the fact that it's coming downward. To solve for the angle, we can start with that. Tangent of theta is going to be equal to the opposite. So from this angle, Vy is going to be opposite over the adjacent, which is Vx. And so we just solved 6.3 meters per second divided by Vy, which is 15. Tangent theta is equal to 6.3 over 15. To get theta by itself, I actually have to take the inverse tangent. So theta is equal to tan inverse. And on your calculator, you can just hit second tangent to get that function. And plug your fraction in, 6.3 over 15. That should get you an angle of approximately 22.7 degrees below the horizontal. It's important to note you should be in degree mode. If you're getting a different answer here and your math looks correct, I would double check that you're in degree mode and not radian mode. We also need to know how fast this cell phone was traveling, and so we'll use Pythagorean theorem. The total velocity, we'll call this Vf, is going to be the square root of Vx squared plus Vy squared. So it's the square root of 15 squared plus our 6.3 squared. If we add those values together, take the square root, we should get a final value of about 16.3 meters per second. So we know the overall velocity has a magnitude of 16.3. We know the angle is 22. We can combine these then and say that the final velocity that it hits the ground with would be 16.3 meters per second at an angle of 22.7 degrees below the horizontal. And that just tells us it's coming downward instead of going upward. I hope that this was helpful for you. If you have any questions, please reach out.